It's a pleasure to introduce our own Elena Murchikova, who is someone who truly needs no introduction. I think the reason for this talk, if I'm not mistaken, is that this is Lena's new member talk.
Yes.
4 years late, 5 years late. Yeah, since she never gave a new member talk. So now that she has departed and is only kind of a visitor, well, not kind of, she is a visitor still here. I think she was finally gracing us with her presence and was going to tell us about her work on the Galactic Center.
I think it's the first time the organizer graced me with the invitation. So yeah, I guess I become the only postdoc at the IAS because never gave a talk at the IAS, the postdoc at the IAS. I gave one when I was a grad student and when I'm no longer a postdoc. Okay, so it is a very friendly audience. I know everybody. So please interrupt me and let's make some fun discussion. And I'll put some idiotic jokes in it, so be careful with me. And if you don't like them, let me know, so I don't deploy them in other audiences. All right, let's start with a few slides of like really basic introduction. That, as all of you know, every big enough galaxy has a black hole in the middle. And those black holes are pretty cool. You know, they produce those jets, they outflows, they shape the environment within those galaxies, and they life. And that's why we like studying black holes. And naturally, our own black hole, our own galaxy is not anything special. It also has a black hole in the middle. And my talk is going to be about our own black hole, but it's not because I terribly like it or something. It's just, I believe that no matter how loudly we scream that we understand black holes and those distant galaxies, where we can actually see them. And then we look at our own one, which we can resolve up to, every star moving, like little clouds orbiting it. And we can't just say, oh, we understand everything, those we can't see, but the one we actually can see, well, it's complex. Let's just forget about it because, we understand everything else. I believe that our ability to describe our own galactic center black hole is the test of how well we understand the physics. Anyway, how in an ordinary field, at least that's what sort of picture we have in our head, how understanding of anything in science kind of works. We have, we approach problems from three ends. We do experiments, we have theory, we have simulations. So experiments feeds, into some information into our community. Theory puts everything it has into simulations. We produce some results. If it doesn't fit with the experimental result, we repeat the cycle and feed this information to black box of our community and understandings come out. But that's not exactly how it works for black hole physics, right? Because the problem is way too messy. Our theory is no longer pure. We cannot just say, well, we can do an analytic solution. It makes no sense because there are so many complex things involved. And even when we do simulations, we can't say, okay, this effect is due to this particular physics we included because it's everything just so messy. So we actually have to couple tightly theory and simulations. It's hard to separate any of them. But that's not the end of it because our observations are also very complex. And to interpret them, we again form our interpretation using the simulations because we say, okay, what sort of things do I expect? And let them feed into our interpretation circle. And that's what we feed into the community. So as you can see, simulations play asymmetrically a central role in all of this. And so let me first show how we tend to simulate black holes and the accretion, and then go put it in the real context of the black holes we actually see and see how well we do. So what we do is that when we want to simulate black hole accretion, we take a black hole we surround it with a torus of material. And this is a cross-section of the tori, because it's much bigger than the previous picture. And then inside the tori, we have initial conditions like distribution of density with the radii, distribution of like how magnetic fields behave. A typical size of tori is a few thousand Schwarzschild radii. The biggest one, at least the biggest one known to me, and I asked around, was 50,000 Schwarzschild radii in diameter, and 25,000 in the radii. And so you have this thing, you set it up, you release your simulation, stuff start falling toward the black hole and form accretion flows, which we then interpret. So additionally, we try to inform our initial condition using observational data. And we use X-ray observation to inform like what sort of gases we have around the black hole, kind of tie those initial conditions there. And with this combination, we come to pretty much two classes of model. One of these models is when you have a lot of material, electrons and protons equilibrate, everything tends to settle in about thin disks. And the second model, which is actually relevant to what I'll be talking about in Sagittarius star, the hot accretion faults, is that supply of material is very little. It's so little that protons and electrons don't meet each other very often. Electrons getting cool because they radiate. Protons would love to get cool, but they just don't meet electrons now. They don't equilibrate, and this thing stays in this shape of like very thick tori with two temperature plasma. This sort of problem been studied for 30 years now, and we again believe we have fairly good handle of what sort of physics going on there. So we have a tori, we inform conditions from X-rays, we simulate them, we get this pretty pictures like this. And what could possibly go wrong is doesn't it all sound very reasonable? One of the issues, which is not the only one, but let's put this one here, is that there seems to be a variability crisis, meaning all of the models are much more variable than the real black holes. Should you be surprised about this? And for the next several slides, I'm going to try to demonstrate to you that you shouldn't be surprised at all, because I'm going to put this thing we simulate into the context of a real black hole, so you can see where all these assumptions actually in the context of real black hole sit, and whether do they make sense.
Sorry, by variable you mean like it's sensitive to choices of initial condition?
I mean, they are sensitive to choices of initial condition, that's part for sure.
Right.
But it's also with time, the flux works more than in the real system.
So for each T, the observed time variability is it seems pretty stable. Is that what it doesn't vary so much?
It's more variable than
It's significantly less variable.
It's significantly less variable than what models.
for all the models, right?
Is that we don't have access to all wavelengths. Is that a wavelength dependent statement? In models of these.
I mean, I don't think there is a ton of as many studies in other wavelengths, but variability process properties are different between which wavelengths you are sitting in. Like in X-rays, it's just like quite quiet, and then that's the flares quite quiet. It's also more variable. I mean, like more variable will show you light curve, and you look at it, it's like, oh, this is more variable. For example, near infrared, the higher frequencies, it's just more variable, it's getting less the lower frequency. All right, and let me now build your galactic center structure by structure. Some of you might have seen this, but some of you, I guess, didn't. So we'll start with a black hole at the center, nothing else. East, west, and wrong directions because you know astrophysics. It's array deck. Everything here is an array deck, so you'll see the galactic plane going through at an angle. It is surrounded by a nuclear star cluster, which is here in gray. It's like clearly extend much further, but the densest part is around 1 parsec. It can extend to 5 parsecs, depends, you know, how you want to count. This is the galactic plane. So the rotation of the galaxy, it comes toward you, goes like this and go into the screen up there. Crosses go into the screen, dot it goes toward you, and you know the arrow. And naturally it's in line because we are sitting in the plane of the galaxy and looking at the galaxy in the plane. So this structure is mini spiral, which is a free streams of the gas, we believe, which carries stuff into the galactic center. Again, this the up one, it goes away, goes behind me, and comes here. This one goes behind me, I'll be the black hole, comes here. And this one we actually don't know. It might not even exist because it might be just a part of the, you know, other structures. So this thing carries the gas with the temperatures between like few hundred, like 500 kelvins to 10 to the 4th Kelvin. This is a circumnuclear disk, also known as molecular ring, meaning it's very cold, from few Kelvin to several hundreds of kelvins. All the structures here to scale, but not in terms of thickness. So again, it goes away there, comes behind me, comes in front and doing this. It's a ring, and we believe it's just inclined, and that's why we see no.
Is it as eccentric as it looks?
Eccentric.
So is it a circular ring or is it a straight?
Assumptions like the models, observational models would be that it is a perfect ring, it's just inclined. Whether it is based on hard to say. So this thing is the clockwise stellar system on which majority of Wolf-Rayet stars live. It's kind of at 90 degrees to everything else because it comes here, right? And goes away there, like little thing. It's a remnant of an old jet. Some might question whether this is exactly the remnant of an old jet. There are many suggestions, but this is like 1 parsec long. You'll see it on future images of X-rays. Let me now zoom in. This is Bondi radii, which is a radii at which thermal energy of gases no longer enough to escape the gravity of the black hole. So this, about identical size to the Bondi radii, is the S cluster. S cluster doesn't have preferred direction of rotation, it's all total mass. So like no preferred direction there. So for the scale, this is the size of SO2 orbit, again in array deck. So it's a projection on the sky. It's about like twice longer if you deproject. And you know, this is a very dense region. To demonstrate how dense this region, I'm going to overlay the distance from us to Alpha Centauri here. It's within the distance between us and our neighboring star. We have a million star cluster and like a bunch of those critical structures. So this is like really dense region. Yes.
The Bondi radius that assumes what temperature is that?
From X-rays. I forgot exactly. Sorry. It's from Baganov's paper, like 2003-ish. It's like 10 to the 5-ish Russian right in this case.
Yes, but the jet. So if it's a jet running, the jet's moving relatively quickly, but it's only a parsec long. Would you not expect anything on scale of parsec to move within years?
I mean, sorry, say it again.
Is this jet supposed to be relativistic?
It's that. It's just like a lively feature. Some people say maybe that's an old jet. Because
Okay,
it's also a parsec, at least, in the projected distance, it's a parsec away. How exactly it is deprojected?
Okay, so maybe like a star from a jet or something.
Yeah. I mean, the statement, people who claim that this is an old jet say that's a scar from an old jet. It just something happened and stopped and there is still special. All right, now I'm going to do another domain. It's again Bondi radii from few Schwarzschild to, this is the Bondi radii here at 10⁵. And I'm going to put the models, how we model the accretion of the torics. This is the biggest tori of 50,000 Schwarzschild radii in diameter. This is a typical tori of few thousand Schwarzschild radii. You see, it's actually, it's like here. It's like for your convenience. And I'm going to put them both together. And this is about like 5,000 Schwarzschild radii, because otherwise you just can't see it at all. And this is like 50,000 sitting there. So you can see that it's kind of pretty small. I'm going to put it in the context of the rest of the structure of the galactic center, and like I chopped the part of it just half. So you can see it's about the size of the S2 orbit, the biggest tori ever existing.
You mean the biggest tori used in simulation?
Yeah, biggest tori used in the simulation as initial condition, because then the accretion flow contrast is like always in. And we say, well, maybe it's not that bad, because don't we inform our knowledge of this initial condition from the X-ray observation? It shows some stars are flying through. Yeah, it's trouble, but we know what we're doing, don't we? So, okay, here's an X-ray image, which is informing your own boundary conditions for tori's. And this is the size of a Bondi radii of such a star. You can actually see that it's about the size of the resolution of the X-ray image. So it's actually informed your conditions right here, 10⁵. And the size, typically you simulate that little guy right here in the corner. So there is quite a jump between 10⁵ to a few thousand. So certain things you have to infer. All right, and another thing I want to point out is that when you look at this image, majority of the structures are actually carrying fairly cold gas from few kelvins, like thousands, to for about 1,000, from like few hundreds to 10⁴ Kelvin. And one thing I want to demonstrate to you, I'm going to overlay it on the X-ray image. And one thing you see, or like more precisely, you don't see, is that you don't see the cold structures on the X-ray. Like at all. Because X-ray is mostly sensitive to about 10⁷ Kelvin. And everything colder than this, if I'm very precise, you can, but you need to have tons of this to be able to see in certain lines in X-ray. So what situation we end up in is that we inform our simulational models based on X-rays and have these tori models. But X-rays only sensitive to very hot gas. Well, at the same time, the galactic center itself is full of much cooler structures, which we totally ignore. So perhaps there is a chance that they also contribute to accretion. We just don't see it and ignore it on X-ray. So let's go with this.
I have a nice question about this Bondi radius. And I am not, we know that it's like 1% of the Bondi accretion rate, the true accretion rate. And so is that,
I would say I think it's less than 10⁵.
So you've taken
-5.
So you've taken that into account. Like when you report like m dot and r, you have taken this factor into account.
We know accretion at Bondi, so accretion is always defined at what radius, right? So when you say accretion at Bondi, every time when you say accretion, you say whatever moves at this radius moves toward the black hole, and you assume that the rest is all away. So
it's not like using the sound speed or. In Bondi radius, you use the sound speed, right?
Yes, but to calculate accretion at Bondi radii, you do use the sound speed of the X-ray, but it's only at 10 to the 5 Schwarzschild radii. And it's not the same numbers when you go close to the black hole. I had those slides, I threw them away, but pretty much if you assume that 100% Bondi falls to the black hole, you get something of order 10 to the 41 ergs per second, of emission from there. You only get 10 to the 36, 5 orders of magnitude. So yeah, you take into account that it's through with slide.
So m dot is inferred from the X range. Observed.
M dot observed one at the near horizon is inferred from polarization measurements.
Sure. Why tori in simulations? I understand they try to mimic some kind of this structure, but given that it looks kind of messy in reality, is it still that
The dominant accretion flow comes from some equatorial plane.
I would assume I would say it's a historical assumptions because at some point, if you look at the galaxies and see like a bunch of material, this is what you do. But at some point, nature really breaks. But still, majority of simulation of accretion are the torus simulation. I mean, when I say majority, I mean like 99.9. All right. So we're going to try to see if there is any contribution of a cold gas to accretion. And actually, I know probably talked about this like in various coffees, but then I looked at the talk I gave, when I was a student, and it was like totally embarrassing. So none of the slides which are here repeating the talk when I was a student. Just point this out. So when I started this project, I was working on neutron stars. Sherwood wouldn't let me lie. He was there. And so, you can't just come to observers and say, hey, people, I want to observe something. They'll say, great, take a walk. We have our own stuff. So you kind of, if you want to get something observed, like to set, have some idea. Luckily, we live in the age of, user-friendly telescopes. So you can actually try to apply for it and learn how to figure out how we're going to use this telescope. And, you go to Mario and they try to figure out, what's this like spectral windows, how you're supposed to align them, what you do use that. So it was a kind of climb from doing, neutron stars. Actually, this is my stupid joke. Thank you so much for it. So the work I'm very grateful to Alma for giving time. And it's data I will show is like from multiple cycles of Alma. And I'm very grateful for them. So to keep giving me time while I was curious. Yes, they didn't know, but that was so nice. Anyway, so that resulted in an attempt to pretty much set the limit of is there any cold gas in this region, just like pretty much hoping to get non-detection. Came up with actually observing some stuff. So you have like a double peak line, red side is offset on one end, blue side of offset on the other end. This circle, conical circle is continuum, and this the colored things are the line emission itself. So like you can see that they all offset from continuum on both ends. What you do things like this, you just start freaking out because like you're totally sure that you did something wrong. And you start checking like all the random things, like for example, does velocity make sense? You just like, you think it's resolved. So what sort of Keplerian velocity is this radius? And your width of the line is about 1,000 kilometers per second, well, and you calculate that for Keplerian motion, it's supposed to be about 1,500. So it kind of makes sense. Can be inclined, right? It can be a bit sub-Keplerian, so that makes sense. Then you put it on this image, and if it would rotate at 90 degrees to all your pole structures, you are in trouble because it would kind of really make no sense. And you see, it actually rotates in this direction of the polar structures because that end goes away from you as for all of them, and like this end comes over you. So that also makes sense. So like then you can calculate what sort of accretion rate you expect from there, just like from assuming that it's made of different clumps collide and they rain on your galactic center. You can then try to figure out if there is enough emission, ionizing emission, to keep that amount of stuff ionized, because that's again not trivial statements. Because people tend to think there is tons of ionized emission around Sagittarius A star, but if you start calculating this, you'll figure out it's actually very little. It's almost producing almost nothing. And actually, majority of ionized radiation comes from Wolf-Rayet stars orbiting at about 4 arcseconds. So if you do like this order of magnitude, what's a typical Wolf-Rayet star emit, etc., what's the distance, how much it's crossing this region, how much being captured by these clumps, you end up that with the numbers that yes, you can ionize this material, but if you look at this, you can also see that we don't have ample amount. Like it's not 100 times more. That's what you need. It's actually almost exactly what you need, and that's order of magnitude estimations. So then another question appeared in your mind: is it possible that there is neutral gas there? If you're barely ionizing what you see, perhaps there is something you are not ionizing, like some clouds which are leaving some neutral gas which are living inside the ionized clouds. And how could you do this sort of experiment? And luckily nature really was kind back then, and it decided to do a flyby of SO2 star exactly at the right moment. So, and the SO2 star, it's a strong source of ionized radiation. I'm not claiming that its radiation doesn't fall in this region, and other times it does. But when it passes, it can give you more photons in some regions and less photons in other regions. So, and it is flying from here, like up there, orange dots, into here. And so you try to see, okay, I'm going to look at spectra and see if I see changes between that time and that time. And if I see changes, maybe I can say how much of neutral gas potentially can be in the region.
SO2 Wolf, right?
No. But it's still, decent amount. I think it will be 2.5, something like that. So we did this work with the Princeton student Tianshu Wang. And surprisingly enough, we did see the change of the spectra. So we saw that one side of the line got particularly bigger. Actually, the closest approach was in May. The biggest emission was in March. Then it was less in April, I think. And then, we don't have observations. So from which, but it kind of makes sense because around March, you don't know the orientation of the disk. At some point, it's supposed to pass, so it gives you tons of photons and fly away. And then if it passes through this region, which is particularly susceptible to, ionization, it still takes months to recombine. So at some point during, like months, it was flying through the region, which was pretty good for you. And then it left. And then within the months, you have time to observe it, and that will be recombining slowly in the process.
You take, sorry, when you take this spectrum,
Yes.
you're looking at some patch of the, you center on the black holes and then looking at some, how big is that patch?
Let me just see if I have that. Okay, I'll go and scroll back. So the patch you're looking at, sorry, so this is the size of your beam. So about like 2 beams across. And, you know, like put 2 beams across on this blue structure. That's the size of the patch of your beam. You're looking at, you know, bigger field on this. But this is your, you know, resolution. Like about 10 beams you're resolving. Everything else you resolve out.
This 20%, like how does it compare to background variability?
So what you're looking at right now, you're looking at the recombination line. The recombination line is few Jansky, few millijansky. On top of this, about 3 or 4 Jansky of continuum. From the point of view of variability of a continuum, it's peanuts. You don't, it's nothing.
How do you know this is significant? This increase is significant.
But you see the spectrum. The rest of the spectrum, it stays, the rest of the spectrum has the same width. And, you know, you have other observations. So it's pretty much stayed the same. Like if you integrate under the curve, it's bigger. It's, you can see that it's bigger. But on the other hand, like, you know, if it was bigger by a factor of 10, you would say, well, something clearly going wrong. But this is, observationally, you're certain in this 20%. But it's not an outrageous number. So potentially it can be more. Maybe, you know, it passed through this patch of like particularly for ionization, you know, 3 months ago, and just whatever remnants I keep recombining. So there is at least, but from the point of view of variability, which look at the answer, you can't, like you are not bothered by recombination line emission.
Yeah. No, if you just like take some background observations of this without the star passing through, do you get like such like this 20% or some similar? That's
not really. Tend to stay close to the like to observations 3 years ago. So there is an observation in between, which has identical thing. So the shape of the line, you know, there's always deep in the middle. The wings, you know, keep around. Okay. So then I think I already said it, but there is drawing. So there is a star passing by. It's you know, like a reddish, pinkish oval there. And there's this composed of like bunch of bumps, and then that's where you are. You'll just like catching more photons or less photons just because like covering a fraction depends where you are for this particular star will be slightly different when you're close to like mid-plane of the distance.
How do you know these cloudlets and all? I mean, there is like some ISM model. Like, how do you know these cloudlets have?
So, order of the sizes of the cloudlets.
Yeah.
It's order of magnitude estimation stuff. Yeah.
I mean, from the ISM theories, we typically don't know, right?
Yeah.
How cloudlets form.
Yeah, pure order of magnitude estimation. Like something which was like makes sense, like 1,000, so some other scale. Yeah, I agree. Then you can calculate how much you know accretion rate you expect, and you know you're not expect like it's all turns out it's very reasonable numbers. I mean, I'm not like doing fine tuning here. Also, you can like you know you have an observation, you can fine tune everything, but then the next observations come in. You have to you know retune an amount of you know if you have to do a lot of retuning, you know you're in trouble. But if you actually not doing much of retuning at all, I think when this observation came in, compared to the previous one, the amount of like retuning was like 10% or something. The numbers shifted a little bit, like sizes of the cloud shift. Okay, and I think I already mentioned that the observation in the middle also have the same shape, except the wings different. So you kind of assume that there is a structure indeed composed of these little cloudlets which are kicked really badly by various winds, by various stars. So you keep more or less the same amount of emission within them. You just like throw them around a little. And as I say, accretion makes sense because this thing falls about 10 to the 4 Schwarzschild radii. And accretion is like 10 to the -7 at this radii from cold phase only. And it's about in between the numbers you would expect from Bondi accretion rate is like 10 to the -6 hot gas, and the accretion at the few Schwarzschild radii where you don't expect any cold gas at all is about like 10 to the -7, 10 to the -8. So you expect a number in between. All right, and now
Image, that's X-ray. Is it Chandra image? The previous slide, that's the previous one.
sorry.
Previous slide. Yeah, this image is from Chandra.
Oh,
Is
no,
it?
it's Alma, it's for me.
Oh, from Almanar. Okay, so this is the same.
No, it's sorry, I should have said like this dotted circle is a Bondi radii. I think I have an error, but like it's not super visible. Yeah. And the size of this thing, it's again got here, which is on scale. So Chandra is much bigger. Chandra resolution is this one. All right, and now I'm putting very long story and everything. Now I'm putting this again on top of this biggest simulated tori, and you see that this structure is about the same size. And you can say, well, whatever, sounds great, right? Because it means like we have the story, like structure, sure, it's like made of cloudlets, but this is what's supplying gas, right? Well, actually, no, because the story was set up in simulation as a hot tori. This thing is totally cold. I mean, 10 to the 4-ish, almost no tori simulation even include cooling at all. So those which do tend to include about up to 10 to the 5 Kelvin. So you're not reaching this temperature. Your initial condition when you set up tori that very hot tori, much hotter temperatures than all right. So, but naturally, from what I just said, you can gather that none of the tori simulation can have any sort of cool structures forming on the scale of the tori, just because they're not set up this way, they're not even include cooling. But do we have things like this forming from other ways? So Shannon still has this simulation of stellar winds. So the purpose of the simulations is actually to reproduce X-ray images. So you put a black hole, you surround it with Wolf-Rayet stars, which you know the orbits of them. They orbit like, more or less. You start blowing winds. You start blowing winds. Let me show you this picture. It's from competing group. They're not doing MHD, they're doing hydrodynamics, but they have this beautiful picture that you start with empty space and a bunch of stars up there. Then stars start blowing winds. Then after some time, there is more winds, and you wait a little bit more, and that kind of the situation stabilizes, and you have some windy structure feeding your body. So those simulations, their primary purpose when they were designed was to see if you can reproduce similar things to the X-ray observations. So this is like what they get, like mock Chandra observations. And this is real Chandra observations. Well, you see the morphology is not at all the same. The average amounts make sense. Like the morphology doesn't, but the average amounts do. So, that's a success and everything. So then back then I asked Sean if he can see something like this cool disk forming there. So he had to lower the cooling, introduce the cooling, run it with the cooling, and concluded that he actually doesn't see any sort of cold structures forming there, just out from collision of stellar winds. The bit of caution here that the competing group, which is in Germany and in Chile, who have hydra, they actually saw the formation of this thing. What you might be a little bit wary about, that it's perfectly aligned with the grid. So we went back to the drawing board and say, fine, Tora is terrible. We tried stellar winds. Let's try something even better. And we collaborated with the student who is now at the University of Maryland. Back then he was an undergrad. We'll say, well, let's do the next step and do even more realistic simulations of the galactic center. So what we need this, big structures which carry cool gas and see, because, if you have supply, you're surely be forming some sort of cool structures and see if we have chance to form them all to just be torn into pieces and thrown away by the winds. So we set the simulation up like this. So we have the stars, they fill the volume with gas, and then at some point we introduce a circumnuclear disk based on observational limits. Meaning people observe circumnuclear disk and they say, well, we believe the average density is this, we believe the radius is this, we believe the thickness is this. So we set this up, and then you watch interaction of the stellar winds with the disk and see what you see. Funny enough, before I'll show you the images from the simulations, when you set it up like this, you actually, you do form the cool disk in the middle, because you have supply of cold gas, and that does have a radius in which it likes to circularize. But also, you see how you can actually form the mini spiral. It's a stochastic process, random things are happening. But you can see that stellar winds can tear pieces out of circumnuclear disk, and those pieces would start falling toward the black hole. And if they are not too small, because when they're small, they're torn into pieces by the winds shortly after they are torn out of the ring. And if they're too big, they would just form accretion disk. But if you tore something like in the mid-size, it actually stretches and shows the structures like this. And funny enough, it was fairly narrow range in which you can get those structures without them being destroyed or whether forming the accretion disk. And if you multiply this funny narrow range by 3, you'll get the mass of the mini spiral. So you can actually pretty much, you set it up with the disk and you get kind of circle mini spiral and this little cool disk up there as well. All right, here's the results of the simulation. So we evolved the stars. Additional thought, here we also have a potential of the nuclear star cluster. None of the previous simulations had the potential of the nuclear star cluster, even where you were already supposed to have it. So this is, time goes this way, it's just a zoom in. So upper row is integrated. Midplane density, and this is just a cut through this is a cut through the midplane, and the upper row is just integrated, like everything within the line of sight. So you set up the circumnuclear disk, and then you see the winds start interacting with this. They blow some part away, and you can see inner side, structures forming, and then stuff is falling toward the galactic center. This is the line of sight momentum. Because the winds are not aligned with the circumnuclear disk, there are some mismatching directions. And this is a temperature plot, and you can see that the fairly cool structures, it's hard to kind of see, but you see lots of like cooler clouds falling toward the galactic center. And again, this is a cut through mid-plane, so if something big was stored and now entering the center, that's why you see some clouds just appearing here.
You know the time scale, like the age of the disk, or
The time scale runs from 10,000 to about half a million years.
in the simulation you've used like some particular.
Half a million. So the reason it's half a million because circumnuclear disk is a transient structure. It's not supported by anything, and it's again like very funny how I met many people who say, but it's a pressure support. It was like, well, no, it can't be. There is nothing there to support it. It is falling into the galactic center, and about after half a million, it starts violently falling into the galactic center. So it is a fair investigation, etc., fair thing to study, but it's no longer study of our galactic center. It's study of our galactic center like in half a million years. So we've pretty much stopped at the point where it's just like violently falling into the galactic center. So you can run it. And somewhere about like 400.4 million years after the introduction of this thing, you start seeing, you clearly start forming like the little clumps earlier, but you start seeing the cold disk around the black hole forming, and it's growing because more stuff falls naturally. You keep this thing growing, and this is a face-on agent. Again, there is no stars to disturb it, so it settles into thin structure. But it's the first simulations, so it's not good anyway. And this is a little thing in 3D when it rotates, and you can see this like dense clumps around it. That's kind of how galactic center looks in the simulations. And before I go, I will spend another 5 minutes on variability things. So you are looking, upper panel is how much, like several hours of Sagittarius star variability in submillimeter, 230 gigahertz. It's like 230-ish. You see how how it looks. It walks around a lot. It's like there is one that goes by one jet ski within 40 minutes, comes back. It's just enough. Just walks around. This thing is we have observations over about 20 years, and you can see that its average is also neither average stays the same. It keeps walking. It walks in. Within years, every thingy here is you take at least 10 observations, which has a mean. You combine them and you see what's going to be the mean value within this periods. It changes, like for example, it's terribly low in about 2000s around.
Sorry, in the top panel, there's this discontinuous jumps. Are there some flares happening? What's that?
Say it again?
The top panel, there's some
The
discontinuous
vertical
jumps.
lines?
Yeah.
A vertical lines is a break of observations.
I see.
Sorry.
I see.
So yeah, you get to the point and then you stop observing. And the one with free with gaps, they just been observed continuously, and there's calibration gaps between. The other one is just have different dates. So we decided to see check variability. So our aim was like look at the typical Tori model and the typical realistic model, which would be stellar wind model in this case. So upper one, it's no, I don't have it. Anyway, the upper one is observations. This one is typical same Tori simulations. This is a typical main tori simulations, and this is a stellar wind simulations. Different set of points as a fast light or slow light. So then you can see that you can just see so much more jiggle in the tori simulations. Either both of them. And when you look by eye in the stellar wind simulation, you see again the flux just walks around slowly. One of the reasons which we pointed in the paper was this. This is a picture of the accretion flow, like 20 RGs in radius. So when you start with a tori, everything is rotating. So you have a lot of time. If some perturbation appeared, it has orbits to develop. And so your flow tends to have to be more like, with the small clumps and everything. While in the case of the winds, you actually do not circularize anywhere. It's a direct fall. You have winds and the stuff is just falling in. It doesn't have orbits. If perturbations appear, it falls in. And it doesn't have those many orbits to develop. So the flow stays much more smooth. Before my conclusion, that's the last slide, which I still didn't figure out how the best way to present, because that's the structure functions and they all look more or less the same. But they actually not. So a structure function is something which you calculate. You have your light curve. You look at the value of the flux at time t plus tau, subtract them, square, and drag this window through the whole curve you have, and on average. So if you look at the main tori simulation, so the circles is observations. If you look at this one, diagonal there, it's it's the same tori simulation. So what you see is that the structure function starts going with the same slope and then deviates after about 3 minutes. Deviation of the structure function means that there are perturbations in the system, there are perturbation modes in the system with periods close to about 3 minutes. And that structure function starts fitting them and it deviates from the line. So you look at the torus simulation, and that looks so much better. It goes, but then starts deviating at the top, it just flattens much more. Again, it fills the modes, and those modes are very strong. It deviates about 10 to the 3 seconds. But then you look at the winds, and we did no parameters tweaking, like 0 parameters tweaking here. It's just there is not much parameters tweaking at all in the wind simulations. You just set up what magnetization of your winds appearing from those, from the stars. And whatever it evolves, it evolves. And you see without any parameters tweaking, they just so much better. They just go, they deviate to the same place. And they just, even by eye, as I showed you before, they just look more like Sagittarius, a star. And so my conclusion is going to be that perhaps if we use unphysical initial conditions, we shouldn't be surprised to get unphysical results. And when we take care of physics, physics take care of us. And thank you so much for being here.
Questions?
What about the variability to second? None of the models seem to go down that far. Is that just a numerical limitation?
You mean that one?
Yeah.
It's a disk space limitation. And they seem to be following this line anyway.
And do you expect the magnetization to be like something that's uniform over the entire domain? Because you're picking a single number for the entire model.
It's a magnetization here for the point sources when it emits at the wings. I mean, the best you can. If you give me better, properties of the Wolf-Rayet stars, you can do it.
But do you expect that to be a universal parameter of Wolf-Rayet stars?
Just something average. It's like, when I showed you calculations of how much ionizing radiation you get, it's like, what's a typical Wolf-Rayet star? There's like a huge range. You just like, okay, let's look at the middle of this range. Yeah, just that.
What about like other wavelengths?
He's jumping. Okay, fine.
Okay. Go ahead. No, I was like, this is the sub-millimeter, but other wavelengths also, like you can put additional constraint.
Interestingly enough, there is more study in sub-millimeter. Oh, sub-millimeter is useful for these people. For these people. And also it's probably one of the most studied ranges. And it's you also can look at the near infrared because that's how the stars attract. But the problem with near infrared, I guess, in terms of hours, they're probably going to be more data there. But in near infrared, in majority of cases, you don't see Sagittarius A star at all. It just goes below detection. So I guess it's just because it's useful for these people.
X-ray, I think.
There are modeling in X-rays. One thing I want to say is that people tend to think that Sagittarius star is monitored all the time. For star tracking, it is monitored actually twice a year for about 3 nights a year. So UCLA goes once around May, once in summer, or in like around September, depends, scheduling the weather. That's how much you get. It's nice if your weather is bad, so it would work. For even like within a period of about 20 years, the reason the structure function ends here, the circles end here, is that you have about 10 observational stretches of this length. It's 3 hours. It's laughable. We have like about 20, maybe about 20, 10, 20, like 17. I forgot which class I did. I think about 20. You have about 23-hour stretches within 20 years. You have less. You can do statistics on everything, but you have even less. So Elias was first.
Oh, sure. I was wondering, you alluded to the connection between forming this disk and the mini spiral. Can you say a bit more about that?
Is there a connection?
Yes, that's what I'm wondering.
I think it's probably, I can just, hand wave here. I believe it's pretty much the same process. Because you get tons of little clouds and at some point they just getting stuck on this little disk. And the mini spiral is just a bigger clumps. They still, like, you don't see the connectors, right? There is no connectors into those streams. They actually don't go to the black hole. Like, at least you don't see them. I guess wind's getting stronger there and you still are getting. I think maybe you're right, because if you get mini spiral, you get your clumps really close. And for you, it's much easier to get a bit more of them into this region. So yeah, I think you're right. I agree.
So does the ELMA data contain some like polarization information? And is that something, because I think some of its modes have that capability, and is that something?
So it does have this capability. It's when it was requested, that didn't cross my mind. It's much, they're much more expensive. Iron overheads are enormous. It gets about a factor of 2. And if you want polarization, it's going to be even more enormous overheads. So no, 30-hour, like about 25-hour proposal would get you about 11 hours of actual observations. So yeah, It's just because of this. I apply for more, I'll try to ask for polarization. And there is no way you cannot reconstruct polarization out of this. There have been attempts in the literature, but they are nonsensical. If you didn't request for polarization measurement, time it just doesn't calibrate for polarization measurement. And it does come in 2 channels by definition, but it's a random number generated.
Okay, should we move the conversation over lunch and
Yes.
thank Lena again?